I got this interesting comment the other day asking if we can show that these two formulae for the dot product are the same by thinking about them as areas, because these are multiplying distances, and this is multiplying distances times a cosine. And the answer is that we can, but it's a little bit tricky because, for example, we're multiplying the x coordinates together, and that's a little bit difficult to interpret because they're both widths. It would be ideal if we had a width and a height, so that might motivate us to rotate one of the vectors by 90 degrees. And that also works out really nicely because this almost looks like the area of a triangle, but doubled. So if we do this, u, v, and if we rewrite cos theta as sine of 90 minus theta, well then this is now double the area of a triangle. So this is double the area of a triangle, because the area of a triangle is a half times the distances times the angle between them. But what does this look like on our diagram? Well, what we could do is let's rotate v by 90 degrees. So if we rotate v by 90 degrees, it might look like this. So you can see the longer side, which is the x value, has now become the y value. So the old x value is the new y value. So we have vx here. And then the old y value, that was the shorter side, is now the new x value, but it's also going to the left, so it's negative. So we have minus vy as the x value. You could also multiply this by a rotation matrix, and you get the same thing. So this is a 90-degree rotation, which means that this angle here is 90 minus theta. So when I say the area of a triangle, the triangle that I'm talking about is this triangle here. Now, we could get the area of this triangle by just doing out the stuff, and you can see that it will be equal to this. You can just draw out a couple of rectangles, but just for the sake of this video, to make it shorter, we're going to use the determinants just to kind of show a couple of connections. So this half the area of the triangle, if we think about doubling this triangle, which we could do by copying, making a parallelogram out of the sides. So if we make a parallelogram, if I copy this side here, and this side here, you can see now we have two congruent triangles. So double the area of the triangle is the same as the area of the parallelogram. So you could get this area by drawing rectangles and just calculating the area. You'll see it's the same as the area of the parallelogram. Or if you're comfortable with the determinants, we can just get the determinant of a matrix containing these two vectors. So we'll put in u first because u is to the right of this vector. So the coordinates for u are going to be ux, uy. And then the coordinates of this vector will be minus vy, vx. Okay, and when we get the determinant of this, we are then going to find the area of the parallelogram. So this will be equal to ux vx minus uy times minus vy, which is the same as ux vx plus uy vy. So basically, the intuition for it is that this term here is the same as the area of this parallelogram. And then the area of this parallelogram is the same as the determinant of this matrix. And because we put a minus here and we flip them around, we end up multiplying the corresponding components together. And that's one reason why the dot product, the two different formulae work, is because you can think about them as areas.